We were looking at advantages of powder processing. One major advantage of powder processing we looked at was cost advantage, and when we say cost advantage, one thing you must keep in mind, if you want to make, let us say, 1 or 2 parts, then this is not the advantage we are talking about, then you cannot use cost advantage. It is only when we have to produce large number of components of the same shape and size, then you will get this kind of advantage, because once initial there is always a investment cost associated with powder processing. As we saw, there are huge equipments involved in this process. So the other advantages of powder processing are listed here. These are related to the properties that you can obtain from the sintered components. For example, by achieving up to 95% density by powder processing, the mechanical and physical properties are comparable with cast materials. So even with the 95% of the theoretical density that you will obtain using traditional sintering for powder processing, you will start to get properties which are mechanically and physically comparable to the properties that you will obtain for a similar component manufactured by, let us say, casting, and in certain cases it may even exceed the properties of casting and may be similar to that of wrought materials. Wrought are the processed material, for example by rolling or something like that. So you may even get properties like that, and that is possible because of several reasons. One is that when you do it by powder processing, the powder size are very small, so the grain sizes you get are very small, so you get high strength, etc. Second is that it is much more homogeneous. Whenever you are doing casting, you saw that there is micro segregation, then there are dendrites. Because of that, there is anisotropy in the properties. Even after secondary processing or after wrought processing, for example by rolling, hot rolling, cold rolling, there is still some amount of anisotropy, which is not there when we are getting the component or the material manufactured using powder processing. In certain cases 99.9% dense structure can be obtained, and what we can also obtain liquid phase sintering, meaning the one of the phases can be in liquid state, and then you can get very dense structure, because then the liquid will be able to impregnate even the smallest of the pores and fill in those, and so you can see that how much better properties you can obtain in powder processing. The properties that you obtain in powder processing, we saw that there is some amount of porosity. So even though you have good mechanical properties, you are getting 95% theoretical density, which means 5% there is porosity. But these porosities need not always be a bad news. You can get some good properties out of it. One of it is damping out vibration and noise property with residual porosity. So because there is porosity, then it also, this particular material when you manufacture using powder processing, is able to damp out vibrations and noise. So you see, it is instead of becoming a drawback, you can use it as an advantage. Ability to retain lubricants. So you remember we said for example in bearings, these porosities can be used as places where lubricants can set, and therefore you do not have to worry about giving extra tolerance or extra space for allowing those lubricants. Because there is porosity, the oil or the lubricant can sit inside that and provide a you can say inherent lubrication to components such as bearings or pistons. So ability to retain lubricants such as lead, graphite and oil, giving less wear and longer life. So you will be able to get less wear and longer life because of these porosities. So keep in mind that porosity in general would be a drawback when we are talking about mechanical strength, etc. But you can use it as advantage in some of the places, and two of those was vibration and lubrication. Achieving a close control of porosity to give a specified balance between strength and lubrication properties. And so you can also design, now that you know that porosity has some advantages, you can design so that your strength is only compromised to only this extent, and in exchange for that you are getting some lubrication properties or you are getting some vibration control properties. So you can achieve that close control on the desired properties by controlling the porosity, which is a superiority over wrought materials. Even other than these, there may be some advantages. For example, improved surface finish. We have already said, we have looked at it, that because we are compacting at very high temperature, you can get very good surface finish and get the contour shapes of the die that you are using. with close control of mass, volume and density. It is a technique for making parts from high melting refractory materials. So even a material like tungsten, which has very high melting point, which you would not prefer using casting technique, can be manufactured using powder processing. High production rates. So once you have invested the cost in getting those press, you can get very high production. You can easily manufacture just by, you have to keep pressing, then sintering, and then you have the component ready. Wide range of compositions for obtaining special mechanical and physical properties. So because you are able to use metals as well as non-metals, so you can get wide range of composition for obtaining special mechanical and physical properties. So this is another very big advantage which we have been emphasizing again and again about powder processing. Now that we have looked at advantages, it is also time that we talk about some limitations. It's not that powder processing can be applied everywhere and for all the kind of materials. So what are these limitations? In general, the principal limitation of the process are those imposed by the size of the part, the compacting pressure required and the material used. So like I have already mentioned when we were talking about the equipment required, so usually 100 to 300 ton equipments are required for those small gears that we manufacture for hydraulic, mechanical parts or automotive parts. But if you start to think about manufacturing very large components, then it would mean you need a very, very large press, and therefore that becomes the limitation. In general, you will those equipment will cost very high, so your cost may become larger than other manufacturing techniques. And even in the press you may have some material which are very high strength, and in that case you may not be able to compact it using your present abilities of your equipment. So these are the limitations. So depending on the size of the press you have, on the size and shape of the component that you are making and the material that you are using, there is only so many components that you can make out of by using powder processing techniques. The process is capital intensive. You remember we are always saying cost advantage, but we have never said that initial cost there is initial cost advantage. Initially you have to put in a lot of capital to get heavy equipments, and there is initial high cost always involved, and that means the production range in excess of 10,000 are necessary for economic viability. These are some rough numbers that you can find through internet when you look about powder processing. So only if you are planning to make some 10,000s of a component, that powder processing may become advantageous in terms of, or may become maybe break even. The dies that will be involved are also very expensive. It's not that you can just try out several dies to find out which particular component is suitable for you. So even the dies are not very low cost, they involve a lot of high cost. The configuration of the component should be such that it can be easily formed and ejected from a die. Undercuts and re-entrant angles cannot be molded and have to be machined subsequently. Remember, we saw all the components that were manufactured were 2.5 dimensions. They did not have any complexity in the third dimension, and that is because of the nature of the process. You are compacting, there is a pressing from bottom and up, so the die can, or the design can have complexity in this plane. You can have whatever complexity you want in this direction, but in the third direction, that is the direction in which you are applying the load, you may not have as much complexity. So you cannot get undercuts, re-entrant angles. So for example, there is some shape like this, so there is a re-entrant angle or there is undercut. These kind of shapes will not be possible, and what you will have to do if you are planning to make such a component is you will make a much more general component, and then you will have to machine it. So in those cases you may have to do the secondary operations, but as far as the overall shape and size is concerned, you don't, it's a near net shape process and you don't need any secondary process. The capacity and stroke of the compacting press and the compacting pressure required limit the cross sectional area and length of the component. So the size is also limited by what is the press size that we have already seen, what is the total tonnage capacity, but it is also limited by the stroke of the compacting press. So for example, if you start to think that I can make a pipe out of it, it is 2.5 dimension in the sense that it has complexity in only this dimension, and this side it is similar in the shape. But if you try to press a pipe like this, then you will find that the total stroke length that is available in the press may be limited, and so the pipes that you want to make cannot be made. So again, the stroke of the compacting press can also limit the size, and this can also limit the cross sectional area, and so this is another limitation in terms of shape and size that can be obtained. All materials which can be satisfactorily cold worked by conventional methods have been produced. So another disadvantage here is that the material should not have so much high strength that you are not even able to compact it, and the usual rule of thumb is that all the materials which can be cold worked by conventional methods can be produced by powder met processing. For example, brass, different alloys of brass or bronze which are copper alloys, but materials which have to be hot worked are not so very successful. Of course, there are several examples, but they are not the most, you can say, the preferred route should not be powder processing, is not usually the powder processing, because the stresses required would be very large even for a small component. And the last and the most important limitation of powder processing is the mechanical properties. So you saw that when we were talking about porosity, that mechanical properties like strength and ductility and toughness are related to porosity. Higher the density or lower the porosity, higher is the strength and toughness. So if you are not able to get very good density, or if your porosity is high for some reason, maybe because you are not able to apply very large stresses, or because your design is such that you cannot compact it more beyond that, then in those cases the strength and ductility will suffer, and so you may not be able to get some structural components manufactured. So design considerations in powder metallurgy. Now that we have understood all the basic introduction of powder processing, it is time we can put together what are the basic design considerations regarding powder processing. Shape of the compact must be simple and uniform, right, the 2.5 dimension rule. So the shape of the compact that you are trying to make must be simple. It can have some complexity in the plane, but not much complexity in the z direction where you are applying the stresses, along which you are applying the stresses. Provisions must be made for ejection of the part. So you remember we could not make re-entrant angles or complex shapes like that, and it was because it will not be, you cannot eject it from the piston after compaction. So the provision must be made for ejection of the part. So when you are designing, you must see that you can eject out the component after taking away, when you have first you apply the stress through piston and then the piston goes back. So after that you should be able to eject your component out of that die. If you are not able to eject it, it means it has some re-entrant angles or some complex parts which is interfering with the ejection mechanism, and so probably you need to simplify the design. Wide tolerances should be used whenever possible. So usually you will get very tight tolerances, but if you wherever possible you should be able to use wide tolerances. Avoid sharp corners, and thus the corners have to be either radiused or chamfered. Now you can imagine that if you have a very sharp 90-degree angle like this, if you press it and then try to eject it, this edge, what will happen to the edge? Edge will be very fragile, because particularly at the stage of green compact where it has not really bonded at the microstructure level. So this can be fragile and can break away. So you have to be, or it will be best if you can make radius out of it or make a chamfer out of it. That way this will no more be your weak point, or it may not break during the making of the green compact. As undercuts and re-entrant angles cannot be molded into the component, these have to be machined subsequently. So you cannot think of any die design where you can have undercuts and re-entrant angles. These must be machined subsequently. The inability of the powder metallurgy process to introduce cross holes. So if you, for example, are looking for a 2-dimension shape like this, but want a cross angle or a cross hole perpendicular to the direction of the applied stress, that is not possible. You can always have a holes like this, but making holes like this is not possible, and such features would have to be machined using a post process step. Punches less than 1 millimeter must be avoided. You are using very large stresses, if the punches that you are using maybe because of the die design that you have. If it is very small, say less than 1 millimeter, then it is very easy to buckle and break. So punches less than 1 millimeter must be avoided. Large sectional changes should be avoided as far as possible, and we will see at one stage that there is a pressure gradient whenever, even though you are applying uniform pressure, but inside the material there is a pressure gradient. So some of the surfaces do not receive as much pressure as the top surface, and because of that, if there is a gradient in the shape, then it will that gets exaggerated. You will have much more pressure gradient, and therefore some parts, some of the cross sections may not be compacted to the same extent as the surfaces, as the components on the top surface, and therefore you should avoid large sectional changes. So as it may lead to cracking of the green component at the change in the section through the transfer of metals. So one is a large gradient and the other is sudden cross section change. Even a sudden cross section change should be avoided, because it can lead to cracking of the green component at the change in the cross section. So you remember at one stage we have to eject out the component, and if there is a very large cross section change, for example you start with 10 inch and then suddenly go to 2 millimeter, then there is a very large cross section change. So one, even when you are applying pressure, it will not be uniform for this 2 millimeters diameter and for this 10 inch diameter. Second, when you are trying to eject it, that green mold may break, and that is mainly because the pressure is not uniform. So these are some of the important design considerations that we need to be aware of when we are talking about the powder processing. So now we have looked at some brief introduction about powder processing. It is time that we move on to the second chapter on powder processing, which is powder characterization. So you remember, this is our overall layout of the powder processing module. So we have talked about the introduction. Now let us get to powder characterization. So when at one stage in the one of the previous lecture, when I started talking about powder, I said you must start thinking about what should be called as powder range, powder or particulate matter. What is that range that should be called as powder, and not, let us say, we cannot call few inches as powder, right? That will be called a rock. If you go a little smaller, then you call them pebbles, and if you go even smaller, you call it granules. So at what size do you think we should call powder? So let us take a look over here on the board, and let us say I have ranges like this. If I make a scale and I say 10 nanometer, is it powder? Then I ask 1 micrometer, is it powder? Or I say 100 micrometer, is it powder? Or if I go, let us say 1 inch, not even 1 inch, we are talking about meter, so let me say 1 centimeter. Is it all powder? Let us say we have not even talked about shape yet. Let us say all of them have similar shape. Let us say all of them are spherical. So can we call this as powder? Can we call this as powder? Or what will be called as powder? That is something you should ask. And if you go through the literature, you would see that this range is usually defined as colloid. These are very, very fine particulates and not usually grouped together with powder. And when you go to this range, this is usually called as granules or granular material. It is this range that is usually classified as powder. So now that we have the range of the powder, let us look at some specific quantities that we may always be interested in. For example, fluidity. What is fluidity? The ability of the powder particles to flow. So if you keep increasing the size of the powder particles, then it becomes easier to flow. You can imagine, you take sand particles or sand granules, and you just take in your hand and tilt your hand. The sand particles start to fall down, and that looks like flow. Sand starts to flow. We always say that sand starts to flow. So that is the term we are referring to as fluidity. So the larger the particle, fluidity will be larger. If it is very, very small, it will not flow. For example, think about the talcum powder. So if you put it like this, it will not fall on its own because the size is very small. Then comes suspendibility. Well, in some liquid medium, for example, it can be water or it can even be air, how easily it can suspend or stay in air balanced. So the smaller the particle, higher will be its suspendibility. You will be able to, or it will be able to hold on its own in the air. So even in over here, there may be lots of these chalk powders which may be floating around in the air. So they are suspended. They are neither falling, they are neither going up. So that is the suspendibility. If it were very large in size, it would have settled down at some corner. If it is very small, the smaller in the size, it is still floating somewhere in the air. So that is the suspendibility. Now when we are talking about powder, let's get a feel of the numbers, a little bit of numbers over here. So let's say we are talking about powder with density 2 times that of water. So it is 2000 kg per meter cube. So it's not a very dense material, it's low density material, 2000 kg per meter cube. And let's look at 3 different sizes. Although 10 nanometer is not a powder, but still we'll consider it for our calculation, just to give you a feel of the number that we are talking about. So these are our 3 different powder size. Now what the number feel that I want to give you is number per kg. How many particles of this size are there in 1 kg? So you take a 1 kg 10 nanometer particle, how many particles would there be? So it is not very difficult to calculate. You can say that it will be 1 over rho into 4 by 3 pi r cube. 1 by rho is the number total volume, and total volume per kg, and divided by 4 by 3 r cube is the number of particles per unit kg. So can you imagine how much it will be? Of the order, I am not going into exact details. So you will get 1 into 10 to the power 21 particles of this size. That is a huge number. And if this particle size was a little larger, about 2 magnitudes higher than that, then we are getting 10 to the power 15. And if you go 2 orders magnitude still higher, you get this size. And this is the range we have described as our powder. So even if you look at the largest particle size, we are still looking at a very, very large number of powder particles. And therefore you would see that a statistical understanding of the size characterization becomes very important, because we cannot identify or individually characterize each and every particle. Each and every particle cannot be, even for a 1 kg particle you have so many billions of particles, and so you will have to have a average understanding or average realization of the characterization. This is one number that you should be aware of or should get a feel of. Another number that you should be aware of or get a feel of is surface area per unit kg. Now if you take a very large sphere, one particle which is of 1 kg, let's say its diameter is r, so its surface area comes out to 4 pi r square. So how much it will be? Few tens of meters square at the most. But when we are talking about particles of this size, 10 nanometer, 100 nanometer, we'll see how much it comes out to, and we'll use the unit meter square per kg to begin with, and this will be nothing but number per kg times 4 pi r square. So we already know the number, we have to just multiply by 4 pi r square to get the surface area in terms of meter square per kg, and meter square per kg, 300,000 meter square per kg. it's not very small, it is, although comparably it is much smaller, it is 3000 meter square per kg. And when we get to d equal to 100 micrometer, which is our largest range that we have allowed for our powder size, then this comes down to 30 meter square per kg. So this one you can see is also very large, humongous numbers. For one particle of 1 kg, few tens of centimeter square, actually earlier I said meter square, it will be few tens of centimeter square if you have just one particle, which will be 0.001 meter square per kg. But when the particle size are of the order of 100 micrometer, we are talking about 30 meter square per kg. So it's a huge number, and therefore since the numbers are very large, the proper unit to use would be meter square per gram. So you just divide it by 1000 and this becomes 300, this becomes 3 and this becomes 0.03. So even for 1 gram of particle of this size, you can see you have 300 meter square. You have 3 meter square of particles of this size, surface area, and 0.03 meter square of this particle size. So if you were to do some reaction at the surface, this is the type of surface area available to you per unit gram. Huge numbers. So this is a very large number, and therefore important that when you are dealing with powders you be aware of it. It also means that if the powder is reactive, it will be it becomes highly active, and it can actually can be dangerous if it starts to burn, because the surface area, so much surface area is available and all of it will start to burn and react. So there can be explosion only if it is a reactive material. So powders can be a little dangerous in that sense. However, this is the kind of number that you should be aware of when we are talking about powder particles. Some of the other parameters that when we talk about powder that you should be aware of are, for example, shape and morphology, chemistry, size distribution, surface area, and even something like compactability, flowability, agglomeration. Now the first of these characteristics, as you can see in the slide, the first 6 of these characteristics are the characteristics of an individual powder particle. On the other hand, the last 3 have been clubbed together as related collective behavior. For example, compactability does not have anything to do with individual particle. Only when you have lots of them put together, then you can talk about compactability. When you talk about flowability, then again it is not one particle. If you just take one particle and try to make it flow, it does not flow. Only when you have lots of these sand particles that you can say it is flowing or not. If you just put one sand particle and say, I tilt my hand, is it flowing? I don't know. You will not have any answer. It is not a individual behavior. And similarly, agglomeration, etc. So let's just take a quick look at some of the shape and morphology, and we'll come back to this in our next lecture. Of course, most of the time we are assuming a spherical particle, which is like this, but that is not always the case. You can get all wide variety, all different kinds of particle shape. Angular, so these are angular like faceted like this, then rounded, so these are small particulates, but they are rounded, they do not have sharp edges. It can even be cubic. For example, think about sugar particles, although they are not still in the size range of the powder, but still you can get something like this. Teardrop, yes, you can get something like this. Sponge or porous, this is very common, particularly if you are using electrolytic process. Acicular, so it is long needle like shapes. Irregular shapes, so basically if you cannot define it anyway, it is irregular. Ligamental, which are long shaped but not really cylindrical. So cylindrical is also long, but it does not it is not squeezed at any point. Ligamental are like cylindrical but squeezed at several points. Then it can be flake, fibrous, polygonal, aggregate, or dendritic. So these are the different kinds of shape and morphology of powder particles that you can obtain during different kinds of manufacturing process of powder. And you should also be aware that depending on what shape you are getting, what is the size range you are getting, your compactability, your flowability, everything will depend, and that is why it becomes important to understand the shape and morphology of the particles. So, we will get back to this same slide in our next lecture to discuss it further. Thank you.